TCP is connection-oriented, which means that it tries to simulate the properties of a physical connection. A physical connection has two characteristics. First, packets arrive in the same order in which they are sent. A good example of this is a point-to-point serial link. When you send packets on a serial link, those packets always arrive at the other end in the order in which they were sent. The second property of a physical connection is that it's reliable. That is, as long as the physical connection exists, any data you try to send using that connection is going to arrive at its destination. TCP uses sequence numbers and acknowledgments to provide reliability and order. When a sender sends a TCP segment, it marks it with an incrementing sequence number. Sequence numbers allow the receiver to reassemble TCP segments in the correct order. When a receiver receives a segment, it sends back an acknowledgment indicating the sequence number. If the receiver doesn't get the acknowledgment after a period of time, it retransmits the segment. If you look at the diagram again, there are multiple paths a packet can take to get from R8 to R5, and depending on the speed of each physical link along the way, those packets may not arrive in the order in which they were sent. In fact, some packets might not arrive at all. They might just get dropped, or they might get mixed up. And not only that, different packets might take different routes. So how does TCP ensure a point-to-point logical connection where packets arrive in the same order in which they were sent? Well, it does so by using three mechanisms. The first is sequence numbers. TCP simply numbers the packets before it sends them out, so that even if those packets get mixed up during transit, the receiver can put them back into the correct order. This is called reassembly. You should be familiar with the TCP three-way handshake, which is how TCP initially establishes a connection. The message that gets sent by a host wanting to establish a TCP connection is called a SYN, or synchronized packet. Literally, it means synchronize the sequence numbers. In other words, here's my starting sequence number. Use this to calculate subsequent sequence numbers for the rest of this connection. Sequence numbers allow the receiver to tell whether a packet has been lost. This leads us to the next mechanism, which involves a system of timers and acknowledgments. If a packet appears to be missing, the receiver can send notification that it's missing a packet. Also, whenever a receiver does receive a packet, it sends an acknowledgment or an ACK message letting the sender know it got the packet and that everything in the packet looks good. Let's briefly revisit the TCP three-way handshake. Again, you probably already know this, but there are some details that are easy to forget. Let's say we have two hosts, host A and host B. First, host A sends a packet with the synchronize or SYN flag set. This packet contains an initial sequence number, which is typically just a random number stored in the sequence number field of the TCP header. Let's say it's 0. Host B then replies with a packet that has both the SYN and the acknowledge or ACK flags set. This packet contains host B's own initial sequence number that is not necessarily the same as host A's. Let's say that this is also 0. The packet also contains in the acknowledgement number field host A's sequence number incremented by 1, so in this case it would be 1. Host A then replies to the SYN ACK packet with its own ACK that has host B's sequence number incremented by 1, which in this case is 1. There are actually two different sets of sequence numbers in any given TCP connection, and again, the purpose of this exercise is to synchronize both the sequence numbers and the acknowledgement numbers. Remember, a TCP connection is a two-way street. In order for it to be useful, packets have to flow in both directions. If the sender doesn't receive an ACK in a certain amount of time, or if it receives a duplicate ACK, it will assume the packet got lost or was severely delayed, and it will resend it. This is called TCP retransmission. The last mechanism is called windowing. Windowing is not like the operating system windowing. This is a form of flow control that regulates the flow of packets to reduce the chances of packets getting dropped because the buffers in the receiver are full. Windowing has some interesting implications and can actually cause the very problem that it's supposed to solve. So, as you can imagine, it's a really good topic for an exam. And we're going to dig into TCP windowing right now.